right is, well, it's got a magnitude and a direction, so what's the magnitude of our right?
In the I-hat direction, and it's half of x.
Yeah. So it's x over 2 I hat cross. My force, well, my force is going to be a current running through a magnetic field, and that's a chapter 22 thing. What is the force running through a current in a magnetic field? Or if you know, remember the force from a charge, we could start from there and rederive it.
What was the question?
What is the force? So I'm trying to figure out what FR is. What is the force on a current, a wire with a current running through it from an external magnetic field?
Is it
F equals Q V cross B?
All right, that's the force on a moving charge.
oh
So we'll put that over here. So the force on a moving charge on Q from a magnetic field is Q V cross D.
F V equals M V squared over R, or M omega over R? What is that, F V? This is from class.
Oh, that is for the charge entering into the magnetic field and it travels in a circle.
Oh.
And those are units.
Okay. Right, yeah, they are.
Ish. All right, so let's do a quick and dirty derivation of it again. So that's Q times delta X over delta T cross B. Shifting it around, so bringing the time over here, we get charge over time, delta X cross B. What is Q over delta T? Charge per time? Charge flows past a certain point and in a certain amount of time. This would be good to know for the test that's coming up. Not
It's
Wednesday.
current.
Yeah, it's current. So that's current. And delta X is just the distance that it goes through, so that would basically be length cross B, where the direction of the length is the direction of the current. So the force on the right-hand side, so FR is equal to whatever my current is, I, and then my length here, Y, the direction, J hat, cross my magnetic field, which is B, I hat. Dramatic pause for questions and people to catch up. So my magnitude here is I've got I, Y, B, and then I got J hat cross I hat. What is J hat cross I hat?
K hat.
Yeah, cross
not k hat.
Negative k hat.
Yes.
I knew one of them would be right.
J hat cross I hat, given our form right here, our system, coordinate system, J hat is up, so I put my hand upwards, because
Okay.
that's the first vector. I want it so my fingers will bend towards the second vector, which is going that way, so my hand goes like this, fingers will go that way.
Right.
Thumb points in the direction of the cross product, which is into the board, negative k hat. So this becomes, it's unfortunate that the x and the cross products look the same. So why don't I add a little flair to the x as opposed to the cross for the multiplication. So times negative I, y, b, k hat. So now I'm left with this I hat cross negative k hat, or actually, we can just do I hat cross k hat and then deal with the negative sign at that point. So what is I hat cross k hat?
J hat. Negative j
You
hat?
know it's gonna be, or is this a, I know it's either positive j hat or negative j hat, and you're just taking a shot?
Well, you said point towards I,
Right,
go towards k.
k is going that way. Yep, negative j hat.
That's what I said.
I hat, it's I cross k, so I hat. So k is going that way, so my fingers need to curl that way. Right hand. Yep,
Okay.
thumb points down. So negative j hat. So I am left with now negative, that negative will cancel out with that negative. I'll put it in there for the intermediate step. So negative I, y, x, b, y, x, b, y, b, x over 2. J hat. The two negatives will cancel out. This. Now, this does make sense. We can think back also is as this thing is rotating around about like that, the rotation is going in that direction. Thumb points in the direction of the torque, which is up, which is the J hat direction, which is what we have right here. Although this is only half the problem. All right, now the other half. This is going really smoothly. Plus, we're now doing this part. What is R left?
The opposite of R, right?
Say it again.
The opposite of R, right?
Yes, indeed. So that would be negative x over 2 I hat. Also, the magnitude is half of the width, which is, the width is x, in the negative I hat direction. Cross product with the force. What is the magnitude of the force? Or what is the force acting on that left wire?
Opposite of that one.
Yeah, it would be. Going through the exact same logic, the only difference is that this is negative j hat for the left-hand side. And so that negatives can cancel out with that negative, and we're left with I, y, b, k hat. We've already done, we did I hat cross negative k hat before, now we have negative I hat cross k hat, the same thing, or negative I hat cross k hat gives you j hat. So plus I, y, x, b over 2 j hat. Well, I just happen to have half of something there and half of the same thing here, so let's just add them together. So we end up with I, y, x, what is X times Y? In the context of this problem.
The area.
Yes.
I forgot to written
It's like-
literally right there.
So part of the reason my going over this is to sort of push our understanding, refresh our memories of torque, and sort of push our understanding of this relationship between magnetic field, reinforce it. But also, I times A, the current. So if I have a closed loop and I have a current running through it, if I take the area of that loop, and yes, I'm making a leap here from a rectangle to any shape, just so long as it's a ring with a current running through it, this is known as the magnetic dipole moment. And because we've run out of letters, the symbol for it is a mu. It is a vector quantity. Thus, the video that I have created called "Do Not Confuse These Mu's."
A lot of you are.
It's my bad, you guys.
So, just as long as I don't have to pay copyright for whatever you play with it. Actually, YouTube doesn't, I think, a fair policy. If there's a copyright violation, then, because one of my videos, I violated copyright, and they said, you know, any proceeds that would go to this, we're gonna go to the artist. Sure. All right, so magnetic dipole moment. It is a vector. The direction of the vector quantity is, of course, a right-hand rule. You go for the direction that the area is going in, or sorry, that the current's going in. Thumb points in the direction of the magnetic dipole moment, which is out. So in this case right here, the magnetic dipole moment is equal to I times A K hat. I know that my magnetic field is in the I hat direction, so whatever I do, as I manipulate this mu and magnetic field, I need to make sure that it ends up in the J hat direction and not erased. So we can generalize it one step further, and that the torque on a loop of current carrying wire is going to be U cross B. And just double check it. So mu is coming out of the port. B is going to the right. So mu cross B puts me in the J hat direction, which is what we found over there. So anyway, fun with torque. G2 Kabuko might be gone from this world, but he forever live on. Can't disease. All right, any questions before we now venture into the fun area of electromagnetism?
You mean this wasn't the fun area?
This wasn't the final?
No, this wasn't the fun area, is what you're saying?
I still miss that word.
You said we're gonna venture into the fun area, so.
Oh,
I was
this is
asking
not
you
the
saying
fun, okay.
This isn't the fun area?
Well,
I had fun.
more fun. It could be of equal fun or more, or greater fun.
I don't
But
think it could be
it's
more
additional
fun.
Additional fun.
And I'm sorry, it would have gone much better had I heard you the first time, and I apologize for.
Yeah.
I was eating M&M's, that's okay.
So we have talked about how a current creates a magnetic field. And actually, the way that, how a current creates a magnetic field, we've talked about electric fields. But what's the relationship between electric fields and magnetic fields? I mean, if I have a charge, it has an electric field. If I move it, it has a magnetic field. So, but can I take an electric field and create a magnetic field? Does it have to be a moving charge? And the answer is no, it doesn't have to be. So Faraday was conducting experiments in the 1820s, 1830s. And he had a loop of wire here hooked up to a galvanometer, which is basically an ammeter, measures current. So let's go for the classic analog ammeter. I've got a needle pointing upwards, and if current flows through it, the needle's going to deflect one way or the other, depending upon which way the current flows. Beside this, he had another loop of wire, and I want to change that. Another loop of wire with a battery and a switch. Pre-Nintendo. And what he noticed is that when he connected the switch here to get a current flowing through this right-hand wire, that the needle over on the left-hand side would flick and then go back to neutral. When he disconnected, the needle would flick the other way and then back to zero. So he recognized that there was some connection between what was happening here and what was happening there. So he plays around with it a little bit more. I mean, you can manipulate sort of how this wire is oriented and how this wire is oriented. And what he realized is that he gets the most amount of deflection when this has the greatest amount of area. So, and then also recognizes he has a current here that's flowing through it. But for the most part, the electric field from this is somewhat negligible, I mean, from the charges, because in essence, once you connect it, the position of the charges changes, but you still have the same net charge. That hasn't changed. So my electric field's not really fluctuating much here, but the magnetic field is. So when I make this connection, I create a magnetic field. That magnetic field is going through, it's all over the place here, but it goes through here, and the needle will deflect whenever the magnetic field is changing through here. Since the area of the wire here, of the loop, seems to matter, we got magnetic field and area. What quantity have we talked about which involves magnetic field and area?
Yeah.
Oh, not that one.
Hmm.
Because magnetic field and area are really independent of each other. We also, just as a side note, dealt with electric field and area.
Oh, that's, I forget the name of the symbol, but it's the same symbol as flux, but then with a B instead of an M, right?
So it
That's
is,
magnetic flux.
without the question mark, yes.
Okay. And it's B dot.
Either B or M. And it is. So I am able to create a current based upon this changing magnetic field. So if I have this changing magnetic flux, because I can make this incredibly skinny. If I had this as, got my meter there, and then I've got it running like this, I'm not gonna get as big a change. So it's not just the magnetic field, it is the flux, it's the magnetic field times the area. So if I'm creating a current, that means there's gotta be a potential difference. And that potential difference, now I have been using delta V for potential difference or voltage. This is EMF. EMF is just an ideal voltage. So if I have a battery with 12 volts, I put my leads on it, it registers as 12 volts. I then actually connect it to a wire so I get a current. I'm not really getting 12 volts worth of voltage anymore, because once the current starts flowing, the internal resistance of the battery or power supply now kicks in. So I'm gonna lose some voltage from internal resistance. The EMF is the ideal. Now, so this is ideal voltage of the power supply. So for what does EMF stand?
Used to stand for,
Electromagnetic field.
but now it.
No, it used to stand for, no, he was off on the end.
Electromagnetic force.
It's not magnetic.
Electro.